Okay, so in this video, we want to look at examples of higher derivatives where it is crucial to simplify before starting to take the derivatives. And you'll see this as you go through examples, that sometimes if you don't simplify it first, as you keep taking the derivative over and over again, the function becomes extremely complicated and sometimes very quickly. So the lesson here is, whenever possible, sometimes it is not possible, but whenever possible, simplify every chance you get before taking the next derivative, as this can save you a ton of work. So in this video, we'll consider four simple examples of higher derivatives where we can perform critical simplifications before taking the derivative. So number one, very simply, we're going to ask to find the fourth derivative if y is equal to 2x to the 5 minus x squared plus 1 over x cubed. So you're given here y as a quotient. Now if you're naive, you'll differentiate this 4 consecutive times with the quotient rule, and this is a real mess. So you ask yourself, before we differentiate, can we simplify? The answer is obviously yes. As we are dividing by a single power of x, we can divide across. X to the 5 over x cubed is x squared. X squared over x cubed is 1 over x. And 1 over x cubed, 1 over x cubed. The question is this good enough? And the answer is, again, no. We have two quotients, we can do better. Do not use the quotient rule here. Bring the x's back on top and use the power rule. Much simpler. And now, the derivative will be performed for each term very simply with the power rule every time. So this will now become a trivial problem, whereas if you try to find this without simplifying first, it would be quite painful. So first derivative, y prime. When you find the first derivative, you don't need the bracket around it. You can just write y prime equals power rule. We get 4x, bring the exponent down, plus x to the negative 2, bring the exponent down, negative 3, x to the negative 4. Here's your first derivative. Let's find the second derivative. Here we can use 2 primes. Y double prime is okay. Equals power rule 4, power rule minus 2x to the negative 3, power rule, negative 3 times negative 4 is plus 12, x to the negative 5. Now here's when you don't want to use again a triple prime. It looks kind of messy. So you write y to the 3 now in brackets. Third derivative, differentiate the second derivative, you get your third derivative. Derivative of 4 is 0. Power rule, 6x to the minus 4. Negative 60, x to the minus 6. And finally, let's find the fourth derivative by taking the derivative of the third derivative. Again, the power rule, so negative 24, x to the negative 5. Negative 60 times negative 6, well, 6 times 6, 36, times 10, 360. So plus 360, x to the negative 7. And there you have it. The fourth derivative is negative 24, x to the negative 5, plus 360 times x to the negative 7. If you wanted here, you could factor, obviously, a 6 from both of these terms, and also put these over positive powers of x, so 1 over x to the 5, 1 over x to the 7. But at this point it becomes more of a cosmetic change than anything else. And if you don't think this was nice, well, go ahead, find the fourth derivative from the original function before simplifying, and you'll see that this will be very unpleasant. Okay, number 2. Same type of problem. Let's find a higher derivative. But before we do, we'll simplify as much as possible. So here let's find the second derivative. So find y double prime. If y is 8x squared minus x plus 2 over the root of x. Well, again here, if you find the derivative from the quotient rule, and then differentiate again from the quotient rule, you're working way too hard. As x to the, or root of x, is x to the 1/2. So, now you're back to the same problem as number 1. Divide through, and use the power rule on each term. 2 minus 1/2, well 2 is 4 over 2. 4 minus 1 is 3, so 8 times x to the 3/2. Minus 1 minus 1/2 is 1/2. Plus 2 over x to the 1/2, bring this back up. 2 times x to the negative 1/2. And now the derivative is trivial, and any higher derivative would be equally easy, as every time we just use the power rule. So let's find the first derivative. Power rule, 8 times 3/2, well 8 over 2 is 4, times 3 is 12. 3/2 minus 1 is 1/2. Minus power rule 1/2, x to the negative 1/2. 2 times negative 1/2 is negative 1. So negative x to the negative 1/2 minus 1, negative 3/2. And here's our first derivative. Second derivative is obtained, of course, by taking the derivative of the derivative. Power rule 12 times 1/2 is 6. X to the 1/2 minus 1, negative 1/2. Power rule, negative 1/2 times itself is positive 1/4. Negative 1/2 minus 1, negative 3/2. Positive 3/2. X to the negative 3/2 minus 1, negative 5/2. And that's it. Here's your second derivative. If you wanted, again, you could send the x's down to have positive exponents, but again, a very minor rewriting of the function. The key is, if you want to arrive at the second derivative, by simplifying first, you have a much easier time than if you did not simplify initially. Let's look now at one other case of division before differentiation, where now the problem is slightly more subtle. So here we'll ask to find the third derivative. And just to remind ourselves of the other notation, I'll use this one. So d cubed over dx cubed of y. So differentiate y with respect to x 3 times, therefore the third derivative. If y is equal to 6x squared plus x plus 3 over 2x plus 1. So, well, you might look at this and say, since we're not dividing by a single power of x, we can't just divide across every term, and so it doesn't seem that we can divide and then simplify so we can find higher derivatives. But if you attack this directly, with the quotient rule 3 consecutive times, things can get quite messy. But we can still divide. If you remember, what we have here is a rational function, a quotient of 2 polynomials. So we can try and perform long division here and see if perhaps this helps us obtaining the third derivative in an easier fashion. And as you'll see, the answer is yes. The function that will resolve from our long division will be much easier to differentiate than the original function. So let's perform this long division. 6x squared plus x plus 3 divided by 2x plus 1. What times 2x is 6x squared? 3x. Multiply across, we get 6x squared plus 3x. Subtract. These cancel. X minus 3x is negative 2x. 3 minus 0 is 3. Repeat. What times 2x is negative 2x? Negative 1. multiply across, negative 2x, negative 1, subtract, these cancel. 3 negative negative 1 is 3 plus 1, 4. And now the degree here is 0, constant term. The degree here is 1. As 0 is strictly less than 1, this completes our long division, which says that the original function is actually equal to, well, the quotient, 3x minus 1, plus the remainder, 4, over the divisor 2x plus 1. So at least if you look at this, what we have is a polynomial, the derivative of which is trivial. There's still a quotient here, but the quotient is simpler than the original quotient. And because we have a constant on top, we can actually avoid the quotient altogether if we bring the 2x plus 1 on top with a negative exponent of 1. And now the derivative of this will be simple power rule with also the chain rule. And finding that the derivative with this form of y will be much easier than this form. So let's go ahead. We are looking for the third derivative, so we'll differentiate this consecutively 3 times. So y prime, the first derivative, 3. Derivative of 1 is 0. Plus 4 is a constant multiple, so it stays there. Here we have the chain rule, right? 2x plus 1 and then to the power of negative 1. So power rule, bring the exponent down, times negative 1. 2x plus 1 to the negative 2. But that only takes care of the negative exponent. There's still the argument, 2x plus 1. And by the chain rule we must multiply what we have so far by the derivative of the argument, and the derivative of 2x plus 1 is 2. And now we have our derivative, which we can write in simpler terms. 3. 4 times 2, 8 times negative 1, negative 8, times 2x plus 1 to the negative 2. Here's the first derivative, easily obtained from the power rule and the chain rule. Let's keep going. Let's differentiate to get our second derivative. Derivative of 3 is 0. Minus 8 stays there as a constant multiple. Again, here we have the chain rule. By the power rule, bring the exponent down. Subtract 1 from the exponent. But this only takes care of the power times the derivative of the argument, which is 2 again. If you simplify, this gives you 16 times 2 is 32. So it's 32 times 2x plus 1 to the negative 3. Well, we have the second derivative. We were looking for the third derivative, or if you prefer, d cubed over dx cubed of y, which of course is obtained by taking the derivative of the second derivative. Very simple. 32 stays there as a constant multiple. Power rule, bring the exponent down. Subtract 1 from the exponent. Chain rule times the derivative of the argument, which is 2. So what do we have? Well, 3 times 30 is 90. Plus 6, 96. Times 2. 2 times 6 is 16. 2 times 9 is 18. So we get 192. So our third derivative, of course with a negative 3, is negative 192 times 2x plus 1 to the negative 4. And if you want here to have a simple fraction without a negative exponent, send this down as a positive fourth power. So our third derivative is negative 192 over 2x plus 1 to the power 4. And notice that every step of the way was very easy. And we found the third derivative without too much work, just with the help of a clever long division first to obtain a much simpler function. And if you think this was a lot of work, well, try and find the third derivative directly from the function without simplifying, and you'll see that this is actually very nice. Let's do one last example using a logarithmic function. And remembering that the logarithmic function, and we'll take the natural logarithmic function, but of course the same holds true for any other logarithmic function. But the idea is that the logarithmic function has very special properties, and we can take advantage of those before taking higher derivatives. So here we'll ask for the fifth derivative. So 5y to the 5, of course in round brackets. Right, if you omit the round brackets, then you say the fifth power, but that's not what we're saying. We're saying differentiate the function 5 times, so don't forget your round brackets, if the function is the natural logarithmic function ln of x times the cube root of x plus 2 times e to the x squared. Okay. So of course, if you differentiate this directly, this will get messy really quickly. And I don't want to even attempt to do it. You can check if you want, but you'll never get to the fifth derivative. We have the ln of a product. And if you remember, the ln of a product is the sum of the individual logarithms. So this will give you that y equals ln of x plus the ln of the cube root of x plus 2 plus the ln of e to the x squared. And you ask, is this the best we can do? The answer is no. The cube root is a power of 1/3. And if you remember, we can move powers outside of the logarithmic function. Ln of x is ln of x. We can move the 1/3 power out, so we have 1/3 ln of x plus 2. Now this is good. And also here, ln and e are inverses of each other. So if you compose ln with e, they cancel each other out, and you're left with simply x squared. And now this is as simple as possible. Now we can start taking higher derivatives. So let's differentiate y. 1 over x plus a third stays there, times 1 over x plus 2. Chain rule times the derivative of x plus 2, which is 1. Nothing comes up. Plus 2x. So here's the first derivative, obtained quite easily. Of course, because we simplified first, then differentiated. Of course, when we look for now the second derivative, don't use the quotient rule here. Bring both terms back up and use the power rule. So another simplification. And the lesson again is every time you're about to find the derivative of any kind of function, always ask yourself, can I simplify or rewrite the expression to make the differentiation simpler? The answer here is yes. And now we'll differentiate using every time the simple power rule. Negative x to the negative 2, negative 1/3 to the negative 2, times, and here we'll see we'll skip the chain rule from then on, times the derivative of x plus 2, which is 1. So here, no need for the chain rule. And this will be true for every consecutive derivative, plus 2. Third derivative, power rule again every time. Derivative of 2 is 0. And here's our third derivative. Let's keep going. Differentiating this gives us the fourth derivative. Power rule again. Taking the derivative one last time will give us the fifth derivative. Power rule. Power rule. And there you have it. Here's the fifth derivative of our function. You could, if you wanted to, put this over 24 over x to the 5, 8 over x plus 2 to the 5. And you could also factor in 8, which would leave you with 3 over x to the 5 plus 1 over x plus 2 to the 5. But at this point, this is more or less just a cosmetic rearranging of the derivative. So you see, by simplifying not only the first time, but the second time as well, we said, okay, we want to differentiate y, yuck. We can simplify, then differentiate, and even when we find the first derivative, we can still simplify so that the second derivative is obtained more easily. And then it was just power rule from then on. And you see, we could have easily found the 6th, 7th, 8th derivative, no problem. Every time applying simply the power rule. And that's it. So the message of this video is, when you take higher derivatives, sometimes you can't simplify, you bite the bullet, things are messy. But there's a lot of examples where if you don't simplify, and this is probably the best example, and you start taking higher derivatives, things will get out of hand. And if you do simplify, things will be very straightforward. So always keep this in mind. Never start taking higher derivatives until you're absolutely certain that the function you are about to differentiate is as simple as possible. And that's it.